So here is the main graphical user interface of our UE to AP demonstrator. On the left hand side, we have the panel to load the data sets, and we also can load it with the open button. The main area has two tabs, one for the online optimizer, which will use this solve button to solve the problem through meta-heuristic online solver. And then the second tab we will look at later is the online predictor tab, which makes use of the machine learning model to do the UEAP predictions. So in the left-hand side of this interface, we have some summary of the optimization score in terms of hard score and soft score. Hard score determines the feasibility of resource availability, the bin packing side of the problem, and soft score represents the optimality, the minimization of the LOS blockages. Here we see the problem state space. Below the green panel, we have the red panel, which shows the network usage in terms of number of APs available and what will be used by the solver. And below it, we see the bandwidth in the terms of required bandwidth by all the UEs and what is the sum of all available APs bandwidth in the network. And below that, we have the link quality information in terms of link blockages. Here we see the number of UEAP association links with 0 line of sight blocker. And ideally, this is for all the UEs in the network. But in cases where we have LOS blockers, we will see the numbers here for 1 blocker, 2, and more than 2. Below the red panel is the blue one, where we have implemented the triggers to simulate evolution in the network, where we can add the UEs, remove them, we can pick them up from the combo boxes where they are populated with their XY coordinates and the bandwidth in terms of in the unit of megahertz required by the UEs. Then we can move them around also in a similar fashion to different locations and change their resource requirements. And here we have also a similar way to add an access point in the network or remove them. So essentially, we can change the whole topology of the network on the fly and see how the solution adapts to it by moving, for example, a ton of UEs in one edge of the network or removing or adding access points in the other edge of the network. In the bottom blue panel, we see the allocation details of the UEAP association solution, and the last table here shows us the detail about each UE. So in this network plot, we will see how the associations are shaped as the solving continues. All these controls are interactive, so they will update themselves. So below the network plot, we see the optimization progress plot and the link quality, which is essentially the same information as here as bar plots. So we will just click the solve button and see how the interface updates itself and how the solver quickly finds the solutions. So very quickly, we see that the hard scores are almost instantly satisfied. So we have now the soft score being improved, which means that associations are being found as shown in the network plot through the lines between UEs and APs, where the blockages are being reduced to 0 ideally. And in case of 0 score, we have already found the optimal score. So we see that we can pause the solver as well as restart it, but it starts from the point where the optimization has already reached, and we can also continue to execute it, let it continue in the online optimization phase while we make changes in the network. So for now, we have already reached the optimal assignments, but let us try to change the network so we can we can add a new UE in this network, let's say at X9 and Y also 9 location. So somewhere around here. And let me just give the bandwidth required as 1.5 megahertz, and I just click the add button. Now behind the scenes, we are invoking RapidMiner data processing and machine learning pipeline, which already executed, and we see the UE is already connected pretty quickly to some of the access points, but there are two. Okay, now there's already one UEAP association with one blocker, and the optimizer tries to continue to optimize that and bring that to 0 as well. Behind the scenes, it's good for us to quickly look at the trigger implementation, which invoked a RapidMiner data processing and machine learning pipeline, which basically invokes the steps of the system model. These are data processing steps. And at some point, we also get the predictions for the line of sight blockers, which are now introduced with the addition of a new UE. And then the results are returned back to the interface. So now we can try to add another UE to the, let's say, location -9x, -9y, and we keep 1.5 as the bandwidth, and we're expecting some UE to be added in this region approximately. So here we go, we have it, and the network has to now find better associations because that introduced also some blockages. What we can do now, we can try to move the UEs that we added and just take it maybe to the other corner. So the UE664 is now also shown in this combo box, and we can try to move it to 9 positive 9 x-axis minus 9 y-axis. So we are moving this one to somewhere in this region, and we just see that it is already the UE1 the second UE that we added has been moved to this region, and now we can also try to change the resource requirement, which was, let's say, for UE663 ID 1.5. Let's increase it to 5 megahertz, and this also introduced some changes in the network because the soft constraint get the second priority, but the resource must also be satisfied, which is the first priority. That introduces some blockages in the network, in the solution, but the optimizer keeps on minimizing it. So this is a demonstration how we can add and change the problem on the fly, and we can verify that yes, indeed the megahertz has been increased to 5 here. So what we can do now is we can try to remove some access points to try to make the problem a little bit harder. So we see there's enough resource available compared to what is required, and that is what we can change to test the method in a more difficult situation by hardening the problem. So I can try to delete some access points, and still we have the solution updates itself, but still we are seeing that the optimal solution is rather quickly found. So let's try to reduce the number of access points to very close to what is required. And at the same time, we can have a look quickly to the access point allocation tables. So right now, the access point 9 has a lot of UEs assigned to it. We can see that here. It can change any moment, but we see that we never, the meta heuristics never overload the available capacity of the access points. So we can continue to create some more stress by deleting a lot more of the access points until the available capacity is reduced close to the required. And at some point we will not be able to satisfy the hard constraints, which will show up here. So let's delete a few more. And so now we are facing a situation where the state space is reduced, but the problem has become harder to solve. So we can try to reduce a little bit more to make the available resource less than 840. And as you see, there are more frequent updates, and the optimization progress plot is also diving down in its performance is affected, but pretty soon the algorithms try to find better and better combinations. So this is how the combinatorial association part is going on. And yet we can try now to add an access point to soften the problem a little bit. We can investigate how the problems change when we would add the access point in a certain region. In this case, I will just add it in the near center of the network. And we see that we can add another one. We are already doing pretty good, but we can now also remove some of the UEs more, some of the access points more, to see um, how much are we able to quickly satisfy the soft constraints. Because due to the deletion that I just did, we are violating now the hard constraints because the availability of resources again dropped. But this way, we a domain expert can examine how different solutions can be quickly reached for satisfying the hard and the soft constraints. And given different triggers, we can test different behaviors. So I'm adding now another access point to make the problem just a little bit easier, but not too easy, and see if we can still reduce the blockages while not violating the hard constraints. So here we have, in this condition, 664 UEs, which are more than when we started. And we are, of course, we are having only 83 access points, and we are using all of them. So this concludes the demonstration for the online optimizer. So we now turn to the second tab of our demonstrator, which is the online predictor tab. Here we will not use the solve button, but we have in the solution quality area the select model option, which is showing us 4 radio buttons for 4 machine learning models. The first one, for instance, is the GBT model trained over 2 data sets, and only the 10% slice of the data was used for training. The second one used 20% of the same 2 data sets. The third and the fourth one have a small prefix O in their name, which means they are optimized, and both were trained on 4 data sets. The first one using 10% of the data for training, and the second used 20%. So these are the 4 models. We trained them in different constellations so that we could compare the quality of their predictions in terms of network use and link blockage quality. So I will just select one, and when I click the predict associations button, we will invoke a RapidMiner pipeline, which does again some data preprocessing and calculates some feature vector before passing it on to the machine learning model to get predictions. And the prediction target is the same. We would like to get the UEs assigned to the optimal access points such that the blockages are minimized and resources are also satisfied. So I go forward and click the predict association button. Meanwhile, this process in RapidMiner Studio is invoked, which will have a data preparation step. As you see here, we are using again the system model, and then once the feature vectors are generated, we choose from one of the 4 models that we have trained, we apply them to get the predictions, and then we invoke a second process, which is shown here, which does some post prediction resolution step and assign the predicted label, assign an actual access point under the predicted label. And so as we get the results, they would be displayed here, and there they are. The rendering shows that the network plot is pretty skewed in the southeast direction. And we see that we use only 63 access points, and only 353, which is the majority by the way, have 0 line of sight blockers, and 159 having 1 line of sight blocker, and 73, 77 have 2 or more. But this is not a negative result in the sense that the model, although has not seen much data, yet is able to predict for the majority of the data points, and there are, given the data set size, more than 82,000 points that were scored. Majority of them are associations where there is no line of sight blocker. But we see here that indeed some access points might have been overloaded. So we can see, although many of these we see right now are not overloaded, but some of the access points, for example here, are overloaded. So we can improve this by choosing to execute some of the other models. We can select the second model and invoke the same mechanism again, and we watch the shape of the network plot and see how the network plot connections seem somehow more balanced when the results appear. Have the results, but the advantage of this machine learning approach is that we can also get predictions for just a certain section of the network or in the center of the network. And so we see that the network plot is already more balanced, right? And so the number of links that were found to have zero blockers has also increased. And also the predictions from this model use more access points, but still we are saving a lot of energy by not using all the access points. Hence we see also that the number of access points that are overloaded, as in this case, are fewer than the ones from the previous case. And so for the majority of the access points, we do not see overloading. So now we have the results from the final model. We already see that the network plot seems much more balanced. It's not skewed in any particular direction. We see that there are 554 UEAP links with zero line of sight blockers. And the links where there are more blockers are also decreasing towards the larger number of line of sight blockages. For example, we have only 20 links where there are more than two line of sight blockers, and we also see that the resource fitting is constraint is being satisfied much better than the earlier model's prediction. Here, for example, we have a very good fit of the resource use, and also we see that, for example, here we have a very good fit, and here as well as in the other highlighted areas. We have a little bit of overloading here, but in majority of the cases, we see that we are not overloading in a very strong way. So that also is a very important result, that we look at the prediction run times, and if we zoom in, we see that the time taken for predicting one UEAP association is only 170 milliseconds, which is quite good and can be also reduced if the models can be further pruned down. That concludes the demonstration, and thank you very much.